So welcome everyone. This is Machine Learning 2. Before I start, I would like to have a show of hands to see how many of you have taken Machine Learning 1. And for those of you who have taken Machine Learning 1, raise your hand. Okay, cool. So I kind of get what kind of demographics here. Okay, so this is Machine Learning 2, and if you haven't taken Machine Learning 1, that's okay, because Machine Learning 2 is kind of relatively independent from Machine Learning 1. Machine Learning 1 focuses on the statistical machine learning and non-deep learning part of machine learning. And Machine Learning 2 will focus more on the deep learning side of machine learning. We're going to see what we are going to cover in this course later in this introduction. So today's lecture will start with cost logistics. We'll give you an outline for this class. And then I will jump right into some machine learning basics. The machine learning basics part, that will be, if you have taken machine learning 1, you're going to find that that's going to be very similar to the first lecture of machine learning 1. But that's okay, I'll just give you a refresher. So let's get started. So cost logistics. What are we going to cover in this course? In this course, it's Machine Learning 2. So most of it will be about deep learning. So we're going to cover fundamental and advanced deep learning models. So this will include multi-layer perceptron. So these are multiple layers of fully connected operations with nonlinear activation. I'm sorry? Increase the volume. Okay. Hello. Is it better? Cool. So we're going to talk about multi-layer perceptron, convolutional neural network, recurrent neural network. So we're going to talk about different variants of recurrent networks. So these are modern versions of it. We're going to talk about GRU, LSTM. Some of you may have been familiar with it, but some of you are not. So we're going to cover very, very technical details. And the homework, I think part of the homework will also cover the details. And we're going to talk about attention, transformer, and batch normalization. So these are like modern techniques to help you to train deep neural networks. We're also going to talk about more on the natural language processing side. We're going to talk about word embeddings, language models, machine translation, and maybe style transfer. So the first three is, some of you may have heard of ChatGPT. In the past several weeks, it has been very, very popular. So they are actually built on large language models and transformer and attention. Right? So we're going to cover part of that. ChatGPT is also about reinforcement learning, but we might not have time to talk about deep reinforcement learning. We'll see. And besides all of this, we're going to also talk about computer vision models. For example, VGG, NetInNet, GoogleNet, ResNet, and maybe even some more advanced application. If we have time, we're going to talk about object detection, object segmentation. So these are the fundamentals and advanced deep learning models we're going to cover in this course. And there will be programming in this course. So the programming part will happen in your homework assignment. All of your homework assignment will be in Jupyter notebooks. And this Jupyter notebook will also be very helpful, as you will see. It's going to be very helpful even when you're doing your final project. So of course, your final project will also be a lot of programming. And the recommended framework, deep learning framework, will be PyTorch. So basically, you're going to build your own toolbox using PyTorch. And besides all of this, we're also going to cover some advanced topics. So these advanced topics, most of it will be about deep generative models. We're going to cover two most commonly used ones. The first set of models is variational autoencoder. The second set is generative adversarial networks, so VAE and GANs. We're going to cover that. And if you are kind of like familiar with the recent advance of machine learning and deep learning, there is a kind of a relatively new direction of research in machine learning and deep learning, and it has been drawing a lot of tensions. If you have heard of stable diffusion or diffusion model, something like that, and that's actually a more advanced version and very related to variational autoencoding. Okay, so these are the things that we're going to talk about. We're not going to talk about diffusion model, but we're going to talk about the basics, the building blocks of diffusion model. So that is the basic VAE we're going to talk about. And if we have time, we're going to talk about a little bit of deep reinforcement learning and a little bit of Bayesian deep learning. We'll see if we have time. Okay. So this is the overview for the course. Before I move on, any questions so far? Okay. Okay. And a bit about me. I did my undergrad in China, Shanghai Jiao Tong University, where I started my research on machine learning, graphical models, and recommender systems. And I did my PhD in Hong Kong, continuing my research on machine learning graphical models. And that's also when we developed a framework of Bayesian deep learning and also applied to recommender systems. And then near the end of my PhD, I went to CMU for a visit. It's a wonderful time. So at that time, I kind of also dabbled a bit on Bayesian deep learning and computer vision. And then I went back for my PhD thesis defense. And then after my defense, I went to MIT to continue research as a postdoc. And there we basically continue doing what I did, like machine learning, graphical model, Bayesian deep learning, and also apply it to some kind of high impact healthcare applications. And here I am, I'm an assistant professor in the computer science department. So these days I, of course, continue my research on machine learning, graphical model, Bayesian deep learning, as well as their applications on healthcare, computer vision, natural language processing, and a lot of others. Okay. So this is me. And about the course, this course will be in person by default, and there will be office hours that are synchronous via Zoom. But you can also, if you need it, you can also make an appointment, request that to be in person in some of the slots if needed. And I will try to leave some time after each lecture as Q&A, such that if you have time, and have questions, you can come to see me in here on stage. Okay, and feel free to post questions on the discussion forums on Canvas, as some of you may notice that if you post questions and people answer to that, and because a lot of people may have the same questions, right? So when you're posting questions and the TA or other students answering the question, it might also be very helpful for other students. Okay, and prerequisite, you may already know the prerequisite for this course is Intro to AI or Principles of AI. The student must be familiar with Python programming. So the assignments and most probably the course project, the final project, will be based on Python, and more specifically, it will be based on PyTorch. And you could use your own computer, sorry for the typo, and you can also use Rugged's iLab or Google Colab to run the code. So we're going to provide some background, but the class, I think, would be relatively fast-paced. Okay. So this is the link for the course website. And if you haven't, please, if you have registered for the course and there's a delay, please try to join our Canvas homepage because the course materials, like the slides, readings, announcement will be made through the through Canvas. Okay. And there will be no textbooks. There will be no standard textbooks. So, but there will be some useful books for you to refer to. Of course, the first one will be the deep learning book by Ian Goodfellow, Joshua Benjo, and Aaron Cooper. So this is basically probably the earliest book that talk about modern deep learning. Okay. And there will be a more hands-on book, D2L, Dive into Deep Learning, and this will also be a very good book. This is more like a series of tutorials. Each chapter is accompanied by a set of Jupyter notebooks that you can play with. So these are basically the two most important books for your references in this course about deep learning. And beyond deep learning, if you're interested, you can also take a look at the PRML book, which is one of my favorite. So this book, it talks more about the content that we are covering in machine learning 1. So most likely, you're going to find it very similar to machine learning 1 content, but it gives you a sense of what the world is like beyond deep learning. Okay, and there's another book, Natural Language Processing with Distributed Representation, that's also worth a read. Okay. For communication, again, please post your questions on the Canvas. So students are actually very much encouraged to post questions and actively participate in the discussions on the QA portal. So try to log into the Canvas discussion forum more often, and if you see other students asking questions, you can also answer that question. Okay. I think that would be very helpful for both of us. So use Canvas for all technical questions and public communication with the course staff. But if you do have private questions, you can email me or the TA, Renhui Wang and Kai Mei. So these are the emails. And we're going to post course announcements on course websites and Canvas. So make sure you check Canvas regularly. Okay. So finally, the work for the course. This course includes 2 homework assignments. So each of the homework assignment will take up 20% of your final score. So these are going to be programming questions in Jupyter Notebook, and it's going to use Python or more particularly PyTorch. Okay, so 20% per homework, and this assignment usually takes a lot of time, so try to start early. And in terms of time and submission, each student have at most 2 late days in the whole semester without losing the score. So after your late days are used up, it's going to cost you 2% of the overall score every day. So for example, if you're 1 day late, after using up your late day, it's going to be 20% minus 2, which is going to be 80%. Okay. So the homework can be submitted in Canvas. You're going to see some slots for you to submit the homework after it's released. So these are 2 homework, and probably there will be an optional homework assignment. So this will serve as extra credit. So the extra credit, the tentative extra credit will be 10%. So this will add up to your original score. So if you are, of course, if you already 100%, then never mind. So these are the optional homework assignment. And the final piece, the largest piece will be the final course project. The final course project will take up 60% of the score. So this needs to be completed as a team of at most 6 students. The recommended team size, however, will be between 3 to 5. Okay. So the work to do, basically, you need, at some point in this course, you're going to be asked to submit a proposal through Canvas, of course. And at the end of the, just before the first presentation, all of you are required to submit a PPT. So this is kind of like a preview of your final project. And also, each team will need to make a presentation. So at the, I think it's in the last 3 weeks of the course, we're going to have like something like a mini conference where people will present their work, and students in the audience can also ask questions and kind of communicate with each other. So these are going to be very fun, and it's probably one of the most interesting period in this course. And after the presentation, you also need to submit a final report. So each team needs to submit a final report. So think of it as a technical report, or if you're a PhD student, you can think of it as a conference, a very short conference paper or workshop paper. Okay, so this is going to be fun and hard work. So any questions so far? No question. Okay. So about the final project, what kind of final project counts? Right. There are several ideas. One of them is that you can try to reproduce results in the papers. So basically, you can try to reproduce the results of some research paper of your interest. So this is applicable only when there is no code made available by the authors or someone else. If there is already code, then you just run the code, and that doesn't count as final project. Okay. So this is the first idea of final project. The second will be like not using novel data set or task. So basically, you're going to develop, for example, develop a network and apply it to a novel data set or task. So this new network is already proposed, but it hasn't been applied for some specific applications or specific tasks. And if this is the case, then you can try to do it, but simply applying an existing model to a new data set, it counts as a final project, and sometimes it might seem too boring. Therefore, you can try to argue, right? Try to argue why your task, why this application is actually a challenge and it's more than what it looks like. Okay. And another idea is do some kind of like a mini research. You can define your own small research projects. For example, you can really develop a new network architecture or a new layer, right? Or even analyzing some classes of models to give people a overall understanding and empirical study or benchmark of a large set of models. That also count as research. And so these three, 1, 2, 3, they all count as final projects, and some combination of them will also count as project files. Okay. Questions?
In the third point, the research project, can we approach you and maybe you have a sub-problem of a bigger problem that we can solve?
Yes, at some point we're going to have some kind of project examples that you can track. Yeah, that would be a good starting point. But you're actually very much encouraged to think of your own research project that really interests you, right? That can make you more motivated to finish the project. Yeah. Cool. Cool question. Any other questions? And of course, for some of you have already taken Machine Learning 1, right? And Machine Learning 1 also has a final project. But try not to use your original Machine Learning 1 final project. But if you want, you can build on your Machine Learning 1 project. But you need to very, very clearly specify what's the difference between your Machine Learning 1 project and Machine Learning 2 project. Okay. What advance you have made beyond your Machine Learning 1 project. Okay. So, and these are some kind of examples of past projects. Just to so that you can take a look what kind of projects. You can see that they cover different kind of applications and use different kind of model architectures, right? These slides will be uploaded to Canvas, so you can all take a look and check. And if you want additional details and instructions, please go to our course website, right? Just click here and there, and you can see some additional details, right? Including the course outline and also some of the syllabus of our course. Okay. Any questions before we move on to the actual lecture for the day? Okay. Cool. Let's move on to the machine learning part. Slideshow. We can start. So this is the actual lecture. So, and again, this course is intended to be a more interactive course. So, at any point during the lecture, if you have any questions, you can feel free to raise your hand and ask your questions. Okay. And I can imagine that your question may very well be the question from other students too. So that would actually help this lecture a lot to clarify some of the points we're missing. So this is machine learning tool. And machine learning tool will, again, will mostly be about deep learning. But before getting into the deep learning, I would like to have a mini lecture or mini tutorial for machine learning. So this is machine learning 101. It's not just deep learning. Just to give you the very, very grand overview. So what is machine learning? Machine learning is actually a subset of artificial intelligence, and it's a superset of deep learning. You can see that if you look at one version of the definition for artificial intelligence or AI, so that's kind of like programming systems to perform tasks which usually require human intelligence. So this is a very broad definition. Right? And machine learning is kind of like a data-driven way of doing that. So in machine learning, people try to train algorithms to solve tasks by pattern recognition instead of specifically programming them how to do it. If you have taken Intro to AI, probably a big chunk of Intro to AI will be about artificial intelligence, but not machine learning. So what is deep learning? Deep learning is a subset of machine learning. It's also a data-driven way of doing things. It trains algorithms by using deep neural networks with multiple layers. So what's deep learning? Deep learning is the deep version of machine learning. So by deep, what we mean is that we use multiple layers, usually a lot of layers of neural network to kind of capture the very, very complex patterns in the data. And to give you a better idea of what's the difference, here we have some examples that count as artificial intelligence or AI, but does not count as machine learning. So one example is the AI chess players using, for example, heuristic search algorithms such as BFS and DFS, or AI pathfinders, like a robotic finding where to get out of a maze, and AI pathfinder using heuristic search algorithms like BFS, DFS, and A-star search. You probably learn some of this during your AI Intro to AI course. So these count as AI, but does not count as machine learning. Right. So it's kind of like in the outer region of this circle. And then What are the examples of algorithms that count as machine learning but does not count as deep learning? So these are actually the main focus of machine learning 1 in the last semester. The examples include decision tree, Bayesian networks, k-nearest neighbor, logistic regression, linear discriminant analysis. So the list goes on and on. So these are traditional machine learning models, but they do not use neural networks. So most of them are actually linear or generalized linear models. Okay, so what are the examples of deep learning? So deep learning, I think all of you will know that any algorithms that use deep neural networks, basically multiple layers of linear and nonlinear operations that count as deep learning algorithm. So this will be the main focus for this course. Okay. Any questions so far? I'm sorry? Data science, good question. So data science can be inside machine learning. It can also be inside deep learning. You can think of data science as a way of using deep learning. It's more like an application. Although you can argue that it's so much more than application. There is also some kind of fundamental methodology in data science. But if data science is using machine learning, then it can be non-deep learning machine learning, or it can also be deep learning machine learning, right? And I'm not sure people would use like the first part, like AI, but not machine learning methods for data science. Most likely, I think that's like, usually these days when we talk about data science, it will be using machine learning methods to do some kind of task. Good question. Okay. Any other questions? I'm sorry? I mean, where can you get the slides, right? Yeah, we're going to upload the slide on Canvas. I'm sorry? Yeah. Cool. Okay. Any more questions? Okay. So here you can, the data science thing is actually a good question because you can think of, so this is your AI, right? And this is ML, and this is deep learning. Right? And actually any kind of AI-related application or field, most likely it will look something like this. Right? For example, this is data science. So data science can use machine learning methods. It can use deep learning methods. It can use AI. But data science also needs something about database, right? Some kind of data wrangling, data processing, data cleaning. And this part is actually not particularly about machine learning. Right? And not only data science, you think about like computer vision or image processing, they also look something like this. Right? Because part of it is about machine learning, but part of it not necessarily about machine learning. Okay. Yeah, so that's try to draw the difference between non-machine learning AI and non-deep learning machine learning. Okay. If there's no more questions, let's move on. Okay. Before going into details, I would also like to talk about some famous and very common applications of machine learning, just to get you interested in the field and motivate you to work harder in this course. Okay, so these are a relatively short list. The list is actually much longer, but this is just some example of what machine learning can do. And the oldest and most commonly used application of machine learning is probably handwriting recognition. So these data set, these are images from the MNIST data set. It's probably the oldest pattern recognition or machine learning data set. The task here is that you're given an image, and the model is asked to recognize what digit this image is. So it's a classification problem. Right? For example, given this image, we're going to the model is going to try to recognize that this is a digit 1, right? And try to recognize that this is digit 7, so on and so forth. So this is handwriting recognition. You can kind of see this is, even in the old days, this can be very helpful in terms of automatically recognizing the handwritten digits. For example, on the envelope of each mail, if the machine can scan the postal code and automatically recognize it, then it can help to automatically kind of sort all these mails through the system and accelerate the processing. Right? So these are one of the applications. And the other application would be object detection. Object detection try to do two things. The first thing is that given an image, try to detect an object. So for example, given this image, you're going to detect that there is something here on the floor, right? And the second thing object detection does is that it try to classify what this object is. For example, after detecting there is something on the floor, the algorithm will tell you that this is actually a dog on the floor. So this is object detection. You try to detect object and classify the object. For example, another example is it detects that there's a bicycle here, right, on the floor, and there's a truck in the back. So these are object detection. If you're familiar with mainstream methods of object detection, you're going to see that there is actually two main categories of methods in object detection methods. One of them is called like one-stage model. The other is called two-stage model. So the two-stage model basically is what I said. Right? In the first stage, you try to detect object, and the second stage you try to classify object. Okay, so this is object detection. Another familiar application would be face detection and recognition. So again, two-stage. The first stage, you try to detect the face, detect where the face is. And the second stage, people may want to recognize what the face is. The face of who is this face belonging to. And you can see some application, for example, if you're using some intelligent cell phone to take a picture, and it's going to try to detect the face whenever there is a face in your frame, and then it will try to use that kind of detection result to help to basically focus better and basically help you to take a better picture. And face recognition is also important. Sometimes it can be used as part of the security system. I can try to see if you're the person who has access to this building. If so, then you can go in. Right? Okay. And another example is document classification. It's also very simple. You're given a document. For example, you're given a news article, and the algorithm will try to automatically tell you what kind of article it is. Is it about technology, or is it about sports, or is it about entertainment? So this is document classification. It's also one of the oldest machine learning application. If you are reading paper, for example, 20 years ago, you're going to see a lot of works that actually does document classification. And one small subset of document classification is spam filtering. So for example, given an email, can you automatically tell me that if it's a spam email or not? So this is a related application. And also clustering. All right, clustering is one of the most commonly used unsupervised learning. You're given a bunch of unlabeled data, and the goal is to automatically split all this data into different clusters. So imagine that your boss is giving you, for example, millions of data points, but you actually don't have the time to explore all these million data points. Right? The one way to do this is that you can try to cluster them. For example, you can cluster them into 10 clusters, and within each cluster, you can kind of like pick 1 or 2 data points to take a look. This would be a much more efficient way, right? So this is clustering. And also super resolution and all the other applications. For example, super resolution, you're given a low resolution image, and it's going to automatically give you a better resolution version of the image. And voice recognition, voice synthesis. If you're using Siri, you're going to know what it means, right? Siri needs to recognize that it's your voice, not others' voice, before it can start do something. Right? So this is voice recognition. And when Siri speaks, it uses some kind of voice synthesis algorithm. And another application is image synthesis. The kind of stable diffusion model that I talked about at the beginning of the lecture, it belongs to image synthesis. And you're familiar with it. Basically, one way to do it is that you give the program a sentence, and the program will generate an image corresponding to that sentence to you. And these days, they're able to do this in a very, very efficient and also high quality way. Like it's going to give you a very, very high quality image. If you haven't tried that out, you can search online. And another milestone development of AI and machine learning is AlphaGo and game playing. Maybe you all know that several years ago, DeepMind developed the first reinforcement learning agent to beat a human champion. So this is one of the milestone events that actually make artificial intelligence and machine learning much more popular than before. And also another related work is DeepMind developed some kind of a deep Q network, right, to actually match human performance in a set of more than 100 Atari games. So this is deep learning in game playing, also very popular. Okay. So after talking about all these different kind of applications, I hope that you understand and you're motivated that deep learning and machine learning are actually very, very useful and interesting. It covers a lot of applications. Okay. And then we can get started with the actual technical part of machine learning. Before I move on, any questions? Okay. Seems no questions, good. So what is machine learning? So whenever we talk about machine learning, we think about 4 things. Think about 4 components of machine learning. So these are data, model, objective function, and algorithm. So what's data? So machine learning, again, the difference between non-machine learning AI methods and machine learning is that machine learning is a data-driven way of doing things, right? So it's using data to automatically discover patterns that you can use to do your task. So data is actually central to machine learning. So, and data can take different forms, right? For example, in supervised learning, you're given a lot of pairs of input and output. So input is X, output is Y. You're given a lot of pairs of X and Y's as data in supervised learning. And in supervised learning, the task for you is to basically to learn a model such that if you're given a new X, then the model can predict what y is, right? An example here is that in here we have 10 data points. We have 10 data points, right? And we have the x and we have the y. And the task here is that if you can learn the model such that if you're given a new x, you can predict what y is. So this is supervised learning. And in this, we're going to come back to this example again and again. In this example, we have 10 data points, right? 10 blue circles, there's 10 data points. And the green line is actually the ground truth. You can think of the ground truth as the way, the noiseless way of generating this data. So if you can learn a model that overlap with this green line, then your model is perfect. So this is supervised learning, and in unsupervised learning, it's slightly different. In unsupervised learning, you don't get the labels, you only get a bunch of x. So you like the clustering example, right? In the clustering example, in a few slides before, you only get unlabeled data, and you are asked to split this data into different clusters. But you don't get the y's, you only get the x. Right? So this is unsupervised learning. And there's also sequential data. So what's sequential data? Sequential data is, you can think of it as a time series. For example, the stock price over the past few months. So this is sequential data. And usually, you would want to use past data to predict future data. Right? But it's actually less clear what is x and what is y, right? So this is, we separate it as a special case. It's a different case. It's far beyond, it's different from supervised and unsupervised learning. Right. Okay, so this is data. And with the data, the second important component, what is it? It's model. All right. So you're given these 10 data points, and the goal is to try to learn a model to predict the new x, predict the new y given new x, right? Then what kind of model you can choose? One typical model for this kind of cases is you can use a polynomial function, right? Because the ground truth, the green line, does look like a polynomial function. So you can choose to use polynomial function. Right? But this is a regression problem. Right? And sometimes you can also use a neural network, or you can also, if it's a classification problem, you can use logistic regression. So these are some examples. And we're going to come back to this with more details later. Okay. And you have, let's say that you have already got your data, and you, in this case, you already got your 10 data points, and you already choose polynomial function as your model. What's next? What's next is that you need to try to find the optimal model, right, given this data point. And one key step of finding the model is to find a good objective function. So this objective function, you're going to learn your model by minimizing or maximizing this objective function. So commonly used objective function include MSE, or mean square error, maximum likelihood, posterior inference, or maximum a posterior. This is just an overview slide. We're not going to talk about a lot of details. All right. Maximum likelihood, posterior inference, and MAP. We're going to talk about it later throughout this course. For now, we can very briefly talk about MSE. So what's MSE? Literally, MSE means you have some kind of error, and you square it, and you take the mean, right? So let's say that, back to this example, right? Let's say that you have 10 data points. So basically, for each data point, you have the ground truth y, right? And you also have your model prediction. So your model prediction, let's call it y hat, right? Then the error that you have is the difference, right? The difference between the ground truth and your model. And you square it. So this is the square error. Right? But you have multiple data points. Therefore, let's say that you have, this is just the error for the ith data point. Then you need to add up the square error for this 10 data point, right? And you take the mean. So this is mean square error. Okay? And you can use this as your objective function. Basically, you try to find a model such that the model can give you predictions that can minimize your mean square error. If you have this most probably is what you're trying to find, right? This is probably your best model. Okay, so this is mean square error, and we're going to come back to this later for a lot of times when we talk about more details about this problem. Okay. And so this is objective function. The last piece is learning algorithm. So when we say that we're trying to find a model such that this objective function can be minimized, right? But how exactly do you find the model? Right? Imagine that your model is let's say that your model is a polynomial function. Then a polynomial function is actually parameterized by the coefficients, right? And how do you learn these coefficients? How do you know what's the best choice for you? So this involves a learning algorithm. The learning algorithm will try to initialize these parameters and then use some kind of different steps to get you the optimal parameters, optimal coefficients in the case of polynomial function. And typical learning algorithm includes, for example, you can use some kind of closed form solution, or gradient descent, or MCMC, or variational inference. And we're gonna, in this class today, we probably will cover closed form solution and gradient descent for this simple case of polynomial regression. Okay? And later in this course, maybe in the advanced machine learning part, when we talk about VAE, we're going to talk about variational inference. MCMC, if we have time, we can cover it, but most probably we don't have time. Okay, so these are the 4 components of machine learning problems. Right? You have data, you have model, objective, and learning algorithm, which tells you how to reach the optimal objective. Okay. And under this learning algorithm, there's also a very important subcomponent, what we call regularization terms or regularization algorithms. So this would include L2 norm, weight decay, dropout, or batch normalization. This mostly is just to prevent the model from overfitting. So what's overfitting, we're going to also cover later in this class today. Okay. Okay. So this is the 4 most important components of machine learning. So again, we're gonna come back to these slides again and again in today or maybe next week's course. So this is a very important slide. And whenever people talk about machine learning, you should always think about what's the data, what's the model, what's the objective, and what's the learning algorithm. And this is not just deep learning, this is also about machine learning, general machine learning. And the difference, I think one one key point that deep learning is getting more and more popular compared to traditional machine learning. Of course, one of the reasons is because deep learning has a very, very large model capacity. And the other key reason is actually in deep learning, especially purely neural network method, the learning algorithm becomes very, very simple. So basically, you construct a neural network, and then you just follow the gradient to learn your parameters. The learning algorithm for deep learning or deep neural networks is typically very, very simple. And this kind of simplicity and convenience make deep learning more and more popular. Okay, so this is the 4 components of machine learning. Any questions so far?
I was just thinking about why A-star, BFS, and DFS aren't considered as NL algorithms. Is it because there is no model as such for A-star algorithm, for example? Like we have data with an objective function, we have a learning algorithm for A-star, but there's like no model.
You can think of it as how do you use the data, right? For example, BFS, you actually do not learn a model. You just search through exploring the model, right? And there is actually also no way of kind of parameterize your model. Yeah. Typically, later in this class, even in this class, you're going to see that what is typical machine learning is that you're given a lot of data points. And these data points, they are kind of like, for example, 10 data points. And you have 10 data points, and you try to have a model to fit these 10 data points. And the model that best fits your 10 data points is your optimal model. You can already see that this is a very, very different paradigm from A-star and BFS, right? Yeah. Cool. Good questions? Any more questions? What's the difference between regularization and what? Learning algorithm regularization. Yeah, good question. And you can learning algorithm try to help you to reach the optimal model, right? Reach the optimal model that can minimize or maximize your objective function. Regularization algorithm, for example, if you look at L1 norm or L2 norm, it actually modifies the objective function. So this is actually very different, right? You can also think of regularization algorithm as under this objective function as well. It kind of modifies the objective function too. I'm not sure if you answer a question or not. Yeah, later in the course, we're gonna in this class today specifically, we will talk about L2 norm, hopefully, and then you're gonna see why this is different and independent from a learning algorithm. Okay. Cool. Any more questions? Regarding what? Oh, sequential data. Cool. So one typical question of sequential data is time series data. Right? For example, this is time, and this is the stock price for Google today. After it announced that it's going to lay off more than 10,000 of its employees, and so this is like price. This is the stock price for maybe 6 months ago, right? 6 months ago minus 6 months. And this is the stock price over the time, right? So this is sequential data, right? If you think about daily data, this is sequential data. And in a machine learning model, people would like to forecast the future stock price, right? Given the history data. Then one way to do this is that you already have this 6 months of data. Then you can train a model to predict the last month of data given the previous 5 months of the data. Right? But you can also use it in another way. You can train your model to predict the last 2 months of stock price given the previous 6 months. So you have different definition of x and y's, right? Therefore, we try to define it as a separate problem rather than just simple supervised learning. Yeah. Anything unclear? Also a good question. So if you're asking about objective function, then if you're forecasting, usually it's also still kind of a regression problem, right? So you can still use this MSE loss, no problem. But in terms of model, you would like a model that's able to take in variable length of input, right? And give you and predict the next output, right? So ideally, this model would be a recurrent neural network. So the recurrent neural network will take in the data one step at a time, right? And then it's going to predict the next step. So we're going to cover a recurrent neural network maybe in the middle of this semester. Yeah. Cool. Good question. Any more questions? Objective function and regularization. So you're talking about objective function and regularization, just these two.
Is there any specific way that all 4 of them need to be picked, or is it that you can use anything with it?
This is also a good question. I think most of the case you can pick anyone. For example, you can choose to use MSE, and then you can choose to try to get a closed form solution or use gradient descent. Right? And particularly in neural network, it's usually just one choice. You pick an objective function and use backpropagation to learn the parameter. The reason is that in neural network you cannot get the closed form solution because it's a very, very complex problem with multiple layers and a lot of nonlinear operations. Right? So in this case, you can think of it this way: if the objective function and the parameter space is really, really complex, then usually the only choice you have is through gradient descent-based methods. But if it's a simple linear problem, then you have more choice. Yeah. For regularization term, it's probably more independent. I guess it's just one extra term. You can think of it as one extra term in the objective function. Yeah. Cool. Good questions? Any more questions? Okay, no more questions. Then let's move on. So this is the first overview slides for machine learning. So literally, if you think about machine learning means learning from data, right? And if you look back to our previous slides, we say that machine learning consists of 4 components. And the first 3 components is, for example, we have a training data, right? Training data, we have a model, we have an objective. We have all these 3. So think of it as 3 different things, right? And you input these 3 different things into your learning algorithm. Think of learning algorithm as a function when you're doing the programming. Right? You put these 3 different things into the learning algorithm. the learning algorithm is going to give you a learned model. So this learned model is the result of your machine learning algorithm. So basically you give this learning algorithm an initial model or initialized model, and this learning algorithm can give you some learned model. And this is the training phase. So after this training phase, you get a good model, supposedly. And then in the real world, the reason that we train a model is for us to predict the output for new data, right? So this is why you have a test phase or inference phase. So in the test phase, you're going to use the learned model, and you're given some input data in the test set. So these are new data that are different from the training data. Right? You're given the input, and the learned model will spit out the predicted output. Right? So this is the training phase and the testing phase of machine learning. And a more concrete example is, let's say that you're given a lot of handwritten digits, right? And you're given, for each handwritten digit image, you also have the label, and you use all these images as your training data to train a model, right? Train a classifier. And after you train a classifier, you go to the test phase. Now you're going to get some new handwritten image. And this learned model will try to classify, to recognize what kind of digit these images have in the image, right? So this is the training phase and testing phase. And you can also see that this is a little bit different, right, from like traditional non-machine learning AI algorithm. Right. Any question at this point?
Does this apply only to supervised learning or unsupervised learning as well?
Good question. So this is more natural if you think about supervised learning, right? But if it's unsupervised learning, it also works. When we talk about unsupervised learning, the typical example will be clustering, right? So in clustering, you are given a bunch of data points, and you cluster them into different clusters. Right? So this is a training phase. But what's the test phase? The test phase is that you're given new data, and you try to find out which cluster this new data belongs to. So this is going to be the test phase for unsupervised learning. Okay. Does it make sense? Cool. Yeah. So that's also a good question. Any more questions at this point? Okay. So this is machine learning and 4 different components. So let's take a step back to look at the first component. Okay. Typically, in machine learning, we will split a data set into 3 parts. Okay. We are going to split a data set into a training set, a validation set, and a test set. So next we're going to talk about what these three sets is. So in the first set is training data set, right? In the training data set, these are the data that you use to train your model. So for example, in the supervised learning case, the training data will be a lot of pairs of x and y's, right? And in the unsupervised learning case, it will just be a bunch of x. Right? And for example, if you're training a spam filter, then your training data will be a lot of emails with the corresponding labels, spam or not. Right? So this is training data. And besides training data, we're going to have a validation data or validation set. So this is also called held out set or development set. And the reason why we need this validation set is that we need this to help us select model. Right? Later, you're going to see that if you only use the training error to select your model, basically every model will be the best because you can always overfit the data set. So you're gonna basically, that's why you need a separate data set to kind of preliminarily test a model to see which model is better. For example, you can to do the regression case, like polynomial regression case, you can choose different model, right? And different model can give you different accuracy, and you can check the accuracy in the validation set to see which model does best and choose that model. So after choosing the model, you're going to have a third set of the data, what's called a test data set. The test data set cannot be accessed during training, and it can only be used to assess the final performance only once. So this is like the real world data, right? After you choose your best data, then you're settled. You deploy the data, and then to see what the actual performance is. So you cannot use the test data to choose your model. So this is, if you do this, then that's usually considered a severe violation of evaluation protocol. Okay. Again, using the test data for training or hyperparameter searches and reporting the result is actually a severe violation of evaluation protocol. So we have the three sets of data: training, validation, and test set. Okay. And later, when we talk about cross-validation, we're going to get into more details on this. Okay. Any questions so far? A typical example would be on short question. Mm-hmm. Yeah, through the validation accuracy. Yeah. Cool. So typically, in deep learning, people will design different model architecture, right? But they are given the same training set. So for different architecture, they can train one model, right? For example, you have 10 different model architecture, then you can use the same training set to train 10 models. After you train it, you can evaluate it on the data, validation data, to see which model is the best, right? And you choose the best one, and that's your decision, right? And then you can test this model, this specific model that you chose, on the test set and report your accuracy. Okay. Any questions? Any more questions? Yes, if you have 10 possible options, right, then you need to go through all these options, and then for each option you have some kind of validation accuracy. Right?
10 different models needs to be developed by 10 different developers.
Sorry.
It will require more work.
Different model. Different model what?
10 different models. So you're taking, suppose we are taking 10 different models and we are choosing the best one among the 10 different models.
Mm-hmm.
But to write code for 10 different models, it will take more workforce compared to the changing the single model itself.
Yeah, that's true. That's true. Yeah. So usually, usually people would just slightly change for example, the number of layers or the width of each layer in a neural network, and you can write some script, right, to kind of automatically run these 10 models one by one for you, or even run it in parallel. Right? So it might seem more work to you, but if you write up a script, that's also very, very efficient for computer to do. Yeah. Any more questions? Okay. So this is the data set. Yeah, this is like the most basic protocol for machine learning, right? And when you're doing your homework or even developing your final project, usually you will need to follow this protocol. Okay. And next, I'm going to briefly talk about different types of machine learning problems. We kind of already briefly talk about supervised learning. Right? In supervised learning, you're given a lot of pairs of input-output data. Right? You have a lot of x and y's, and y is the label, x is the input, and you train the model to predict y from x. Right? So this is supervised learning. And in unsupervised learning, you only get the x. Right? You only get the x. You have a lot of x, and you're going to let the model to learn something. For example, you can learn a clustering of the data set. So this is unsupervised learning. There's another learning paradigm or machine learning model, or machine learning problem that's called reinforcement learning. So reinforcement learning is a little bit different. It involves sequential decision making with delayed reward. So what's delayed reward? If you think about supervised learning, right? When you are learning the model, you're given the x, right? And the model will predict something that's called y hat. And immediately, the model will know whether it makes the right prediction or not, right? Immediately, the model will know the y, basically what's the difference between the ground truth y and your prediction y hat, right? So this is immediate reward. And then you can use some kind of learning algorithm, right, a gradient descent to backprop, and then update your parameter immediately. But in reinforcement learning, this is not the case. In reinforcement learning, let's say you're playing a Go game, and you will not get your final reward until the end of the game, right? You need to play the game for a lot of hands before you get the final reward. So this is very different from supervised learning, and of course very different from unsupervised learning. And it requires a lot more effort to make the learning algorithm work, to learn the agent. We might not have enough time to cover reinforcement learning, but if you're interested, you can go to the course website. We have some reading materials for you. Okay, so this is reinforcement learning. And another interesting, relatively new learning problem is self-supervised learning. So self-supervised learning is kind of like, you can think of it as, it's kind of related to supervised learning and also unsupervised learning. One typical example of self-supervised learning is learning to predict the future. For example, in this time series, right, you're already given this time series. You don't need any label because the time series itself contains a label. It just depends on how you split the time series, right? You can split it here and use the first 6 months as x and the last 2 months as y, right? Or you can split here to use the first 2 months as x and the last 4 months as y. So this is self-supervised learning. Now we can think of the difference between self-supervised learning and supervised learning is the key word is self, right? What do you mean by self? Self is that the computer itself will generate the labels for you to train the model. In supervised learning, right? In typical supervised learning, us human would have to generate the label for the computer to learn it. But in self-supervised learning, the computer, human will develop some trick and will tell the computer to create the labels. And then we're going to use the labels, the computer-generated label, to train our model. So this is the typical example that I mentioned. You have a video. Right? This is called a moving MNIST data set. You have 3 digits moving around the screen. So this is the video, right? This is the data. And us human can tell the computer to split the video such that we're going to use the last 2 frames as Y and use all previous frames as X, right? And then the computer will do so and automatically split the data into X and Y's. And then we can train a model to predict Y from X. And this is self-supervised learning, right? Computer generate the labels for us. And this is also another form of self-supervised learning. If you look at these different crops of images, you're going to easily define that this small image in the top left is actually coming from the same image with this image. Right? So basically, another way of creating labels is that you can take one large image and slice it into different crops, right? And you can tell computer to do so, right? And when computer is slicing it, they know exactly which slice of sub-images come from the same large image, right? So they have the label. And then you can train a model to recognize, right, which pairs of images are coming from the same large images. Right? So this is also another example of self-supervised learning. And it turns out that this kind of algorithm actually works very well and can do it. Question? I'm sorry? Yeah, that's a good question. Yes, in the old days, people used to call it unsupervised learning. There's actually some kind of previous work before self-supervised learning is introduced, and the paper called it unsupervised learning too. Yeah, so that's why I say self-supervised learning is kind of related to unsupervised learning too. So the key idea is that you ask computer to generate labels for you, and you train using that computer-generated label. Yeah. But yeah, it's very, very closely related to unsupervised learning. If you think about unsupervised learning means that you don't need human annotation. You don't need label. But self-supervised learning, they actually need label. It's just that the label is generated by the computers. Does it make sense? Cool. So any more questions? Mm-hmm. Let me see. It's possible to, for example, pre-train your neural network using self-supervised learning. Let's say that you have a lot of digits, right, handwritten digits, but you actually do not have the labels. But you can use self-supervised learning to automatically create the labels, like by slicing images and then asking the model, let the model to recognize which pairs coming from the same digits. After you do this, you already train a good backbone network, right? And then you can fine-tune your network with the label data using supervised learning. So that would improve your performance. Right? And this is a good question, because this is also how people use self-supervised learning. Because self-supervised learning, they can help you to basically pre-train the model, but to really do something useful, you should need to you're gonna need to fine-tune your model to do the task you want. Right? Any more questions? Oh, previous slide. This one. So imagine that you're trying to predict. So this is a video, right? It's a video of 3 digits moving around the screen, right? You can see that this movement is gradual, right? And how do you create, like automatically create labels such that the model can train on this data? You can tell the computer to use the last 2 frames as y, right, as the model output that you want to predict, and use all previous frames as x. So this is the input that you input to the model. And then you can train a model. This model will take the previous 7 frames, right? Previous 8 frames as input, and the model will try to predict the last 2 frames. Right? You're gonna choose some kind of objective function and learning algorithm to do that. Right? And after you finish training the algorithm, what you get is actually a very nice model that can predict the future. Right? You can even make the prediction in a rolling basis, right? Given the first 8 frames, you predict the last 2 frames, and then you can use all previous frames to make predictions for even further in the future. Right? So this is also counts as self-supervised learning. So before the word self-supervised learning exists, people call it unsupervised learning. Yeah. Any questions? I'm not sure this makes sense, or do you have any more follow-up questions? Okay, cool. So self-supervised learning, we have one last example of self-supervised learning. It's the simplest one. So basically, you're going to tell the computer program to rotate the image by some random angles. And then when the computer is rotating the image, right, it knows by what angle it's rotating. Therefore, the computer itself has the label. And then you can train a model to predict the rotation angle of the image, right? Then this network is useful because it kind of extracts useful middle layer representation. And after you pre-train a model using this kind of self-supervised learning tasks, you can then fine-tune the model with any specific task that you're interested in. Right? So this is some very high-level, simple idea of self-supervised learning, but I think it kind of already covers the most important part. It's a simple idea. I think everybody can understand it. Questions? I'm sorry?
We generally do homographic
Homographic
adaptation.
adaptation? Oh, what do you mean by homographic adaptation?
I mean, like scaling the image, taking the rotation.
Oh, yeah. That's doable. Yeah, you can kind of scale, but scaling is, I'm not sure, but scaling is a good question. You can scale the image larger or smaller, and ask the model to predict the size of the image. Maybe it's doable. Yeah, people have developed different kind of operations to create labels. So rotation is only one of them. You can kind of smear the image or kind of add some kind of random noise into the image. So these are also different kind of augmentation to an image. That also counts as self-supervised learning. Yeah. Cool. Good questions? Any more? Okay, cool. So this is self-supervised learning. I hope you all get it. And so the last one, also kind of related to both supervised and unsupervised learning, semi-supervised learning. So what's semi-supervised learning? Semi-supervised learning is kind of like combination. It's very direct combination of supervised learning and unsupervised learning. So in supervised learning, you get all the pairs of x and y's, right? And unsupervised learning, all the model appear only you only have the x. So semi-supervised learning, only a part of the model will have the label. So only a part of the model will have both x and y's. But for other models, you only have the x. So more concretely, for example, your first data will be x1, y1. Your second data will be x2, y2. x3, y3 is your third data. But afterwards, you only have x, but you have no y's. So this is semi-supervised learning. Right. In semi-supervised learning, only part of the data have labels, and all the others, you do not have the label. So one question is it really necessary to consider semi-supervised learning? Right? If what you want is to train a classifier to predict y from x, can we just ignore the unlabeled data and only use this data to train our classifier? Would it be the same? Or would considering this unlabeled data actually improve your performance? So this is a key question. And the answer depends on your data distribution, incorporating oftentimes incorporating the unlabeled data will actually help you to train a better model. So let's consider an example. Okay, let's say that we try to train a binary classifier to classify positive data from negative data. So, and this is your positive data. This is the pluses. I have the minus. So these are the negative data. Okay. So in this case, if you only have labeled data, and then the natural decision boundary, basically your model, will be here, right? Your model will, after you learn the model, your model will say that any point that is to the right of this line would be positive data, and any point that is on the left of this line would be negative data, right? So this is supervised learning. But what if someone tell you that, wait, I have a bunch of unlabeled data as well, and it might help. And it turns out these unlabeled data, they are here. So we are going to draw this unlabeled data using circles. Okay. So in this case, what would be your optimal decision boundary? If you know this unlabeled data, then maybe in this case, you would think that your optimal decision boundary is actually here, right? And this is actually very different from your original decision boundary, which is here. So this is the original one. This is your new one. So having this unlabeled data can actually help you to refine your decision boundary and get you a better classifier, get you a better model. Right? Any question at this point? Are you convinced that this is better or not? For those of you who are convinced this is better, then raise your hand. No one's convinced? Any questions? I see a question. I'm sorry? After what? You generate label for the rest of the data. I'm still don't get the question. You mean how do we use this unlabeled data? Mm-hmm. Oh, we're going to use the same model class for example, linear model. Yeah. So we can, the way this works, you can think of the way this works is that you can usually people would do some kind of what we call label propagation. Basically, you're gonna, so these are the unlabeled data, right? These circles are the unlabeled data. And you're gonna propagate these positive labels gradually to this unlabeled data, right? So basically, you can propagate this label to this unlabeled data and basically mark it as positive data. But only, the key is that you know that this label you get is from label propagation, so you have a lower confidence of the label, right? But still, you're gonna propagate the label, and then in this part, it's gonna be negative data, right? And after you propagate the label, you're gonna train a new classifier. So this is your new classifier, right? And most probably, this new classifier is gonna be better than the old classifier. Right? So any more questions? So this is just a high-level overview. I hope this questions. We're not generating now. We're not generating new. I'm sorry. How does this work? Yes. Compared to using only the labeled data, you are now using this unlabeled data, right? So you have more data, and this more data can help you to refine the decision boundary, right? So the assumption is that there will be some kind of gap between positive and negative data, right? And originally, this is what we have, right? Originally, this is your gap, right? Then you're gonna put the line here. But after observing new unlabeled data, you're gonna see that the gap actually kind of move, kind of rotate, right, from here to here, right? So after getting this new unlabeled data actually help you to find a better decision boundary. Questions? Yes, you can think of it that way. That's one way of propagating the data. Yeah. And this semi-supervised learning is a big field. It kind of became popular maybe 10 or 20 years ago. And there's a lot of different algorithms to propagate the label. And using unsupervised learning, for example, clustering them and propagating the label is one of them. There is also other kind of label propagation methods. For example, graph-based label propagation. So graph-based means that, for example, for each data point, you're going to find your nearest data point, and you're going to only propagate the label to your nearest data point. But when your nearest neighbor, so if your point, the distance between your point and the nearest data point is too far away, then you're going to propagate the data, but with lower confidence. Right? Now, there's people come up with different ways to propagate data and for this semi-supervised learning. Yeah, but this is just to give you a very rough idea that there is this new different machine learning problem for semi-supervised learning, and using unlabeled data can actually improve performance. Okay, any more questions? You mean the distance is the same, right? That's a good question. So that's also what semi-supervised learning try to understand. And maybe one good choice is to ignore the data points because it has equal distance, right? Yeah. And if you randomly assign it, it just create more noise. So you might as well just discard it. Yeah. Any more questions? Okay. So this is semi-supervised learning. See the time here. Let's take a 10-minute break, and we're gonna resume at 1:58. Okay. Now let's get back to the class. Testing. Okay, let's get started. So in the first half of the lecture, this is where we are, where we talk about different types of machine learning problems. So we kind of cover semi-supervised learning, self-supervised learning, supervised learning, unsupervised learning, and reinforcement learning very, very briefly. So these are different kind of machine learning problems, right? And next, we're gonna dive deeper into the first type of machine learning problems, which is supervised learning. Okay. So in supervised learning, it's probably the most commonly used and simplest type of machine learning problem. So in supervised learning, you have two typical tests. Right? You have classification tests and regression tests. Okay? So more formally, what's a classification test? A classification test takes something, for example, an image or text as input, and it tries to output some y which is categorical, or someone may call it nominal. So this y is actually a discrete variable. For example, you can have multi-class classification, say classifying object types, digit classes, right? And typical example is here. Right? You're given some kind of digit images, and you'll try to recognize which digits it is, or you're given some kind of images, and you'll try to classify whether it's a cat, or it's a bird, or it's a deer. So this is multi-class classification. And even a simpler form is binary classification, where you only have two classes. And for example, in a spam filter, you try to classify if an email is a spam or not. So this is only a binary classification problem. So this is classification. And in regression, it will take similar input, for example, an image or text, article, document, something like that, and it's going to output a real value. So this y is a real number. So in reality, there are a lot of cases that you need to predict a real number. Right? For example, like what we said before, predicting the stock prices, or predicting electricity consumption. So predict stock prices, we all know that is very important, right? You can make money if you can predict the stock price. And electricity consumption can also be important, because energy company, if they can predict the electricity consumptions early before a surge of usage, they can plan accordingly, right? And this planning can actually save money for them. So this is predicting stock prices. And in computer vision, there's another typical task which is called age estimation. It's also a regression task. Given an image, you try to kind of estimate the age of the person in the image. For example, this is the image of Walt Disney, and a good model will estimate that this is kind of like a man in his 60s. and the accurate number would be 62. Again, treat it as a real number, so this is a regression problem. Okay? So this is classification and regression. Any question at this point? It should be clear that what's classification and what's regression. Okay. So this is, in general, they are all supervised learning. So in supervised learning, usually people will use parametric supervised learning. So what's parametric supervised learning? Parametric supervised learning means that your model is actually parameterized by some parameters. So usually people will use function approximation. You can think of your model as a function, right? You think of a model as a function f. This function f, so each function will take something as input, right? So this function will take x as input. So this x can be some feature, some attribute, some covariates, right? And this function will output something. So this function will output y. And this y, people call it response variable, call it target, call it table. So basically this model will predict something for you, and we call it y. And a concrete example would be the model f can take an image of a digit 7 as input, right? And the output of the function can be digit 7. Right? So this y says that this is digit 7. So this is a classification problem, and this model is parameterized by a set of model parameters. So usually we call this model parameters theta, and it's in the subscript of f. So model parameters are hyperparameters. So this is parametric supervised learning, and it's a very high level slide. But more concretely, let's come back to our polynomial curve fitting problem. So you can see that this is a regression problem, and in this regression problem, you get 10 training data points, right? And again, the horizontal axis is input, right? The vertical axis is the output. Okay? You get 10 data points. And then this is machine learning, right? You're going to ask our typical question: what's the data, what's the model, what's the objective function, and what's your learning algorithm? This is your data. And your model, we're talking about polynomial curve fitting, so we're going to choose polynomial function as our model. So this is going to be our model. Our model says that given the input x, we're going to use a polynomial function to guess what y is. So this is a polynomial function of order m. Right? And this polynomial function, if you look at it, for a polynomial function of order m, we have m plus 1 parameters, right? W0, W1, all the way to Wm. So we have m plus 1 parameters. So your polynomial function, your model, is parameterized by this m plus 1 parameters. So this m plus 1 parameters is actually our theta in the previous slides, right? So theta, in this case, is your wi. So I is from 0 to n. So you have m plus 1 parameters. And so this is your model, right? You have the data, you have the model. So what's next? Next is that you need to, let's check the list, right? The next is that you need to decide on an objective function, right? And then you're going to minimize or maximize the objective function to learn your optimal parameter. So in this case, this is regression task. So we're going to use MSE as our objective function. This is slightly different from MSE, but it's actually very similar. You can see that our objective function is just a sum of capital N terms, right? And in each term is the difference between y of xn and w minus tn. So this is the difference between our prediction and the ground truth label. Right? Tn is the ground truth label for the nth data point. Y of xn and w is your prediction for the nth data point, right? And in all following slides, in all lectures, usually we're going to use boldface to represent a vector. So this boldface w is actually representing a vector containing m plus 1 entries. So this is a vector containing w0, w1, all the way to wn. Okay. So this boldface w is a vector. So basically, this boldface w is your parameter, right? It's a parameter for this polynomial model. And we say that we want to use MSE. So this is going to be the square error, right? And instead of taking the mean, because we have 10, here we have n data points, right? If you use MSE, then you can go with n minus 1, right? But here we use 1/2. So do you think that this is equivalent or not? For those of you who think this is equivalent, raise your hand. Okay, for those of you who think this is not equivalent, raise your hand. Okay, so the answer is it's actually equivalent in this case, because for us, we want to learn the optimal W, right, that can maximize this error. And whether you have 1/n here or you have 1/2 here, it doesn't really affect your answer, right? Because n, 1/n or 1/2, this is just a constant term. Right? So it does not affect anything. So that is why we choose 1/2 instead of 1/n, because it's convenient mathematically when we derive the closed form solution later on. And you're going to see why. But for now, just bear with me that we're going to use 1/2 because it doesn't really matter. So here, this is our objective function, right? And now we have the third component of our model, right? The third component of our model, we choose some variant of MSE as our objective function. Now the next question is, how do we minimize the objective function? This is error, right? This is mean square error, so we want to minimize the error. So how do we find the W that can minimize the error? We need a good learning algorithm. So how do we do it? As promised, we're going to talk about two learning algorithms. So one of them is gradient descent. And this gradient descent is actually more closely related to deep learning algorithm. As we mentioned before, you basically all deep learning or deep neural network learning uses gradient descent, or more specifically stochastic gradient descent. We're going to see the difference later. So the idea of gradient descent is just to take the gradient of the error with respect to our parameter, and you take you kind of move your parameter along the direction, along the opposite direction of the gradient. And with a proper step size, you actually guarantee that you can make the objective function smaller. So let me give you some intuition on the blackboard. So let's say that. So this is our W, right, in the horizontal axis, and we have the E of W. This is our error, mean square error. And for example, let's say that in a very, very simplified case, in reality it's much more complicated, but here we simplify it into a very low dimensional space. So let's say that the whole landscape looks like this, and you initialize your W here. So this is your initialized model. This is your initialized model. Right? And the next step is that you're going to take the gradient, right? You're going to take the gradient of the objective function with respect to W. What does the gradient look like? The gradient looks like this. So it points towards this direction, right? The gradient is actually positive. And using this equation, we're going to move W to the opposite direction of the gradient. Therefore, we're going to move in this direction, right? With a proper step size, you're going to move this. So originally, you're in this W, right? With a proper step size, you can move this W along this direction, and hopefully you're going to end up here, right? If you end up here, then this is already a lot smaller than the original objective function, right? So this is gradient descent, and you keep doing that. You keep doing that until you get a good point. And usually you're going to end up in a local minimum. And the reason why we say that you need a proper step size is because imagine if you are here, let's say that you are here, and you take, you're here, and you take a step size that's way larger than needed, and you move in this direction, and probably you're going to end up here, right? If you end up here, then that's a huge overshoot, because you actually end up increasing your objective function, which is bad. So that is why we say that this step size needs to be proper, okay? And in this polynomial case, it's relatively simple. You can always search the optimal step size, right? Because you can get the gradient, and you can choose some kind of step size, and you can try it, right? You can try it to see whether it actually decreases. It actually decreases your error. If it do decrease your error, then you just keep moving on. But if let's say that you're here, and you happen to choose a step size that's larger, and you see that it actually increase your objective function, then you're going to backtrack, right? You're going to go back to your original point, and this time you're going to try a smaller step size. And you try it again. Maybe in here you're going to try a smaller step size, and it's going to end up here, right? If it ends up here, then you're in a good shape, right? Because this time it actually does decrease the objective function, and then just keep moving on. So this is gradient descent, okay? You can see that this is relatively simple, easy to implement, and the intuition is very straightforward. So a lot of people use that. And in deep learning, people also use that. So in deep learning, people don't use this kind of backtracking thing. People use a relatively smaller step size, but over the years, we have developed very, very clever algorithm that can automatically decide the step size. So usually, you don't need to worry about that too much in deep learning. Okay. So this is gradient descent. It's relatively simple. Ultimately, you're going to get to in this polynomial curve fitting, if you use gradient descent, ultimately, you're going to get to a optimal solution. Okay. Any question so far? So, okay, gradient descent, very general, and we're going to come back to this maybe several lectures later to tell you what kind of clever approach people have been developing to automatically kind of adapt the step size. Okay, so this is the first learning algorithm that we'll talk about. This is a gradient descent. The second learning algorithm is closed form solution. So this is going to be mathematically more involved, but it's still doable. Let me first give you an intuition of closed form solution. So what's closed form solution? Let's say that so in this case, in the original case, we have 10 data points, right? And we try to fit a polynomial curve. Let's say that we have a simpler case where we have 3 points. We have 3 data points, and we try to fit a polynomial curve. And we try to fit a second order polynomial curve. So we're going to try to fit ax squared plus bx plus c. And we're trying to try to do this. And we only have these 3 data points. Right? So in this case, one way to do this is that you can use gradient descent, right? You can use gradient descent and use this as a prediction, and then you can just keep optimizing. Let me write this into another notation. Maybe that's easier for you. So this is going to be W0, and this is W1, right? This is W2. So we're going to use gradient descent to keep updating W. So in this case, the bold-face W is W0, W1, and W2. Right. You can use gradient descent to gradually update your W until you reach the optimal solution. But in high school math, we know that given 3 points, in general, given 3 points in a 2D space, you can actually write down the exact solution that can fit these 3 points. Right? It's actually second order polynomial that can fit these 3 points. Right? And if you follow high school math, you can actually do it exactly. Right? Basically, you're just solving a linear equation system. Right? You have this is x1, y1. This is x2. This is y2, right? And x3. This is y3. And then you can simply say that this y1 is equal to w2 x1 squared plus x1 w1 x1 plus w0. Right. So this is the first equation. The second equation x2 squared w1 x2, right? You can see where this is going, right? Plus w1 x3. So you have these 3 equations, right? And y1, y2, y3, x1, x2, x3, they are not they are all known variables, right? So basically, you have 3 unknowns. You have 3 linear equations. Therefore, you can actually solve this linear equation to get a closed form solution for the optimal W, right? So this is closed form solution. You don't need to go through iterative process to get your best solution. So this is probably the simplest example for closed form solutions. And in our polynomial curve fitting, things are a little bit more complicated because it's going to be a, let's say that it's going to be higher order, and sometimes you're not going to have matching linear equations and number of unknowns. For example, you have 10 data points, but sometimes you only want to fit a third order polynomial, right? So it's not going to be that easy. But anyway, we can develop some ways of getting and learning the optimal W such that we can minimize the objective function. And to do this, if you look at this equation and look at this objective function, we have all the xn and we have all the tn's, right? And what we're trying to do is to try to find the optimal W, both-phase W, such that this objective function can be minimized. To do this, the first step we have is to write it in the matrix form. And after we write it in the matrix form, we can use some linear algebra to conveniently solve it, right? Conveniently solve for the optimal W. So the first step is to write it in the matrix form. How do we do that? Here we provide an example. Let's say that we have 3 data points, and we try to fit these 3 data points with a second order polynomial. Right? This is actually exactly what we have in here, right? But we're going to think of it in a different way. Okay? So if we have 3 data points and we set m to be 2, right? Then how do we write it in the matrix form? Let's do it. So let's say that we have a matrix X. This matrix X contains our input data and different orders of our input data. So this X is, let's say this is 1, x1, x1 squared. So this is our matrix X, okay? And we have a W. W is both-phase W, is our parameter. So here we have W0, W1, and W2, okay? We also have T, right? We're going to concatenate the label of these 3 data points into a vector, right? T1, T2, T3. So T is going to be equal to T1, T2, and T3. Now, our claim, I can tell you that this objective function can be conveniently written in the matrix form using this equation. To see why, let's just do it step by step, okay? Let's first take a look at what will happen if we have x times w minus t, okay? What will happen if we have x times w minus t? Let's first check what is x times w. So x times w, x is a 3 by 3 matrix, right? W is a 3-dimensional vector, right? So basically, but it's a column vector. You can think of it as a 3 by 1 matrix. So ultimately, what you get is, if you multiply them two, you're going to get a 3 by 1 matrix, right? Or a vector, or a 3-dimensional vector. And the first entry of this 3 by 1 matrix, or 3-dimensional vector, is going to be the inner product between this one, these 3 values, and these 3 values, right? So it's going to be 1 times W0 plus S1 times W1, right? So we're going to write it in different order. And x1 squared times W2, right? So this is the first entry, right? And the second entry, you can kind of see where this is going. The second entry is going to be all the same, except that this is for x2. And the third entry is going to be about s3. Right? So this is the product of matrix X and W, right? And we're going to minus T, right? Going to minus T. This is going to be T1, T2, and T3. Right? So this is what we have if we do x times w minus t. Okay, and this is a vector, right? And what's this thing, right? What's this two double vertical line? We have a 2 in the subscript and then 2 in the superscript. This is called L2 norm. And by definition, if you have a vector v, the L2 norm of this vector v is defined as the square root of the sum of each entry's square. Okay, so let's say that you have this vector v. Let me plot it here. This vector v is three-dimensional. Then the norm, the L2 norm of this vector v will be the square root of v1 plus v2 square plus v3 square. Okay, so this is L2 norm. Okay, but here we have a square. So the square of L2 norm is the square of the square root, which is just the sum of square for all the entries. Okay, so this is the square of L2 norm. Now back to this case, right? We are in here. We write it as the square of the L2 norm of this vector, right? So what's the square of the L2 norm of this vector? The square of L2 norm of this vector is going to be what? It's going to be all this thing, we take the square, right? So basically, if you take the L2 norm and take the square, right, you're going to, no, let's not do this. I'll write it one more time. If you take the square, if you take the L2 norm and take the square, it's going to be the square of the first entry, right? So the square of first entry, what's the square of first entry? The square of first entry is here. The square of first entry is actually our y of x1 w minus t1 square. Right? So this is the square of our first entry, right? And the square of our second entry is y of x2 w minus t2, right? And we have the third component, right, which is the square of the third entry. Therefore, we know that this matrix form is actually exactly the same as this objective function, right? So in this way, we actually double check that we can rewrite this objective function in a matrix form. So this is our matrix form. And this is the first step of deriving the closed form solution. Any questions so far? Okay, so this is the first step. The first step, we are convinced that our objective function can be rewritten in a matrix form. So the second step, what we're going to do? In the second step, we're going to take this matrix form of the objective function, and we're going to take the gradient of this objective function with respect to w, and we're going to set the gradient to 0. After setting the gradient to 0, we're going to get some equation, and then we're going to solve that equation. We're going to solve the equation and get our w. This w is going to be our closed form solution. Basically, the intuition is that if, again, we have this plot, right? This horizontal axis is w, and this objective function looks like this. Basically, you're looking for a point where the gradient is 0. Right? You're looking for a point where the gradient is 0. Right? If the problem is convex, then if you look for a point where the gradient is 0, that's usually your local minimum. And if the problem is strictly convex, then that's actually your global minimum. So you can actually use this, just set the gradient to 0 and solve for a solution that's going to be a closed form optimal solution. So next, we're going to see how we can take the gradient and solve this equation. Okay. So now you're convinced that this matrix form is correct. Now all is left is to take the gradient. Take the gradient of the objective function. And how do we do that? So we have the objective function, and we say that this is equivalent to SW minus T square root, right? And this is vector, this is vector, this is a matrix, okay? And before moving on, we need to take a look at another equation. If you look at W here, W is a vector, and the square of an L2 norm is actually the sum of each entry, right? Another way of writing this is that you can actually write it as the transpose of W times W itself. Right? To see this, if you take the transpose of W, sorry, not the transpose of W, transpose of V. Okay? If you take the transpose of V, then you're gonna, so V is a column vector, right? If you take the transpose of V, you're gonna get a row vector. So this row vector is gonna be V1, V2, V1, V2, and V3, right? And times this column vector V1, V2, V3. Right? And so V transpose, this is V transpose, this is V, right? If you add them, if you multiply them, that's going to be exactly this, right? So the L2 norm, the square of the L2 norm is actually equal to V transpose times V, okay? I hope this is convinced. Now, we're going to apply this. We're going to apply this to this form. Okay. Remember that this whole thing of S times W minus T, is ultimately going to be a, this part before the L2 norm, right? Before the L2 norm is actually a column vector, right? And we're going to take the square of this L2 norm. Then we can actually write it as what? We can write it as this whole thing is transpose times this whole thing, right? Right? And now we can kind of expand it into different terms, right? If we expand it, that's going to be something like, I hope you still remember your linear algebra. So we're going to take this transpose into this whole equation. Right, so this is the next step. Okay. And then you're going to, so this is 2 terms times 2 terms. So ultimately you're going to have 4 terms, right? Let's see which 4 terms you have. So the first term is this one times this one. So we have, so this is your first term, right? And the second term would be minus W transpose T transpose T, okay? And the third term would be this one times this one, right? It's going to be T transpose times W, SW. The last term will be T transpose times T, okay? So we have 4 terms. And you can go back and check that these two terms, they are actually the same, okay? We're not going to go for the details here, but you can just break it down and check that these two terms, they're actually the same. The reason why it's the same is because if you look at this term, it's actually a scalar, right? It's actually a 1-by-1 matrix. Then for a 1-by-1 matrix, the transpose of a 1-by-1 matrix is itself. And if you take the transpose of this one, the transpose of this one is actually W transpose XW T, right? So these two, they're actually the same, right? So these two, we can combine it into the same term. Therefore, what we're going to get is going to be this one times X times W minus 2 of this, right? 2 of any of this. And we're going to use this one. So 2T XW plus. Now this is what you get. And this is your objective function. And you're going to take the gradient of this objective function with respect to W, right? How do you do that? You're going to take the gradient of these three terms 1 by 1. First of all, you're going to take the gradient of this first term with respect to W. How do you do that? Then this would involve a set of what we call vector derivative. Let's go back to an example. If you have V transpose V, V transpose times V, and if you want to take the gradient of this one with respect to V, what you're going to get is actually just 2 times V. Okay? This is actually very similar to a scalar case, right? In a scalar case, if you have x squared and you're going to take the gradient with respect to x, it's going to be 2x, right? And in the vector space, it's actually the same. So we're going to use this, but we're going to generalize it much more because in here we have a matrix in the middle here. And it turns out if you take the gradient with this thing with respect to W, the gradient would look like it's going to be just the middle matrix here. So the first term, let me write it down here. We're going to take the gradient of the error with respect to W, right? And the first term is the gradient of this one with respect to W. And the first term is this one times W. Okay, so this is the first term. The second term is the same. This is a linear term. This is a linear term. So basically, if you take the linear term, you take the gradient of this one with respect to W. What you have is, so we're going to have 2 here. And what you have is minus 2. You're going to need a transpose here and T. Okay, so this is the second term, the derivative of the second term. And if you look at the third term, it's actually the easiest because the third term is irrelevant, right? It's a constant with respect to W. So the gradient of the third term with respect to W is actually 0. So ultimately, you only get these 2 terms, right? Now we come back to the reason why we want this 1 over 2. We want this 1 over 2 because we have the 2 here. We don't want this 2 here. Therefore, we have this 1 over 2 right here. Okay. And if you use 1 over 2, then you cancel out all the 2. Then all you have is just this as your gradient. And now if you set your gradient to 0, you can finally solve for your optimal W. So you can solve your optimal W by just solving a simple linear equation, right? and you just take this one to the left. That's going to give you something like exactly this one, right? So this is going to be your optimal W. Okay. Any questions so far? Is it clear enough? So if not, you can take a picture and you can go back home and just double check yourself. And this is probably the most mathematical slide in this class. And it involves some kind of vector calculus and vector derivative. And a good reference book for this kind of operation, if you are a little bit rusty about your linear algebra, you can refer to this matrix cookbook. I'm going to put the reference here. And the slides will also be uploaded to Canvas so that you can check. So this is the closed form solution. The closed form solution can give you the optimal solution in one shot instead of going through an iterative process to get the optimal solution. Okay? And with that, I guess this is it for today's class. Again, I'm going to upload the slides, so no worries. And if you have any questions, feel free to come to us, either after class or in the office hours. Okay, cool.